R136 is a young concentration of stars at the heart of the star cluster NGC 2070. It acts as the main source of light and energy for its host nebula, the Tarantula Nebula, which is a cloud of mainly ionized hydrogen and is one of the largest known nebulae. The nebulae itself resides in the Large Magellanic Cloud, the Milky Way's largest satellite galaxy. It contains over 70 O-type and Wolf-Rayet stars, which are the most massive and luminous types of stars known. The concentration is located about 1,600 light-years from Earth, causing the group to have a very low apparent magnitude and apparent size, so it's very faint and difficult to observe. Because of this, none of the stars inside R136 or the group itself are visible to the naked eye. The group may be faintly visible using 10 by 15 binoculars under typical conditions. However, you wouldn't be able to make out anything, as the sheer brightness of the stars and their visual proximity together from Earth makes them impossible to see. Resolving the stars requires much larger professional telescopes. But what makes this seemingly random group of stars so special? To answer this, we must look at the group's extreme properties. The group has a mass of about 90,000 times that of the Sun. For reference, the Pleiades, which is one of the most well-known and well-studied star clusters, has a mass of 800 times that of the Sun. But aside from all the gas throughout the concentration, where is all that mass coming from? Let's take a look at the members of this group. The brightest and most well-known member of the group is R136A1. It is a Wolf-Rayet star located in the R136A knot of the group. It is widely known for possibly being the most massive and luminous star discovered as of June 2026. But how extreme really is it? If you took every star within 20 light-years from Earth and combined all their masses, R136A1 would still be 7 times more massive, at 291 times the mass of the Sun. However, it loses about 0.00016 solar masses per year. And how bright is it? Imagine you counted every asteroid over 1 kilometer wide in the asteroid belt, even the undiscovered ones. You would count around 1.5 million of them. Now imagine for every asteroid you counted, you made a star identical to the Sun. Now repeat this process 4 times. Even after all of that, you would still need around 1 million more stars to match the luminosity of R136A1. A luminosity 7.2 million times that of the Sun. There is also some evidence that it is a binary star, as a paper from 2022 suggests that the star HSH9517 is in a binary system with R136A1. Another Wolf-Rayet star that resides in R136 is R136A2. Like R136A1, it is located in the R136A knot of the group, and is also extremely young, luminous, hot, and massive. The star has a mass loss rate of 0.000046 solar masses per year. Although this may not seem like a lot, this is actually around 625,000 times more than what the mass loss of the Sun will be during its red giant stage. It was predicted to have started out with a mass about 500 times the mass of the Sun, but has since dropped to a mass of about 195 times that of the Sun. As it loses its mass, it heats up its core, which promotes very fast hydrogen fusion through the carbon-nitrogen-oxygen cycle, or CNO cycle, which is one of the 2 sets of fusion reactions where hydrogen turns to helium. This results in a very high luminosity, at over 5 million times more luminous than the Sun. In fact, it produces more energy in 10 seconds than the Sun does in a year. R136b is another star located in R136. Unlike the stars we've covered so far, this one is classified as an O-type main sequence star. However, some other studies classify the star as a hot supergiant instead. R136c is a possible binary system located in R136. The primary star is another Wolf-Rayet star, and we don't know much about the possible companion. Much like the other stars in R136, it is extremely massive and luminous. It has a mass that is about 142 times that of the Sun's, and a luminosity around 3.8 million times more than the Sun's. But how did the R136 group form? Let's find out. The R136 region likely formed from the rapid collision of 2 H1 regions, which are gas clouds composed mainly of neutral atomic hydrogen. The stars formed from condensing gas in the heart of the Tarantula Nebula, with the lower mass stars forming first, at 4 to 5 million years ago, and the higher mass stars forming last, around 1 to 2 million years ago. But what about the future of the group? NGC 2070, the cluster the group lies in, has a very high mass, suggesting it may potentially turn into a globular cluster, a very densely packed group of stars. But the stars themselves also have a very interesting future. Let's take R136A1 for example. Typically, when Wolf-Rayet stars deplete their supply of hydrogen in their core, it is thought they evolve into luminous blue variable stars, a rare type of large, hot star which undergo massive fluctuations in their brightness. However, some Wolf-Rayet stars with sufficient mixing from their core to their surface may entirely skip the LBV stage, turning into hydrogen-poor Wolf-Rayet stars. At the end of its life, R136A1's mass would have dropped to around 50 solar masses, a sixth of what it is today. Overall, R136 is a very interesting group of stars, located in one of the largest known nebulae, and containing some of the most luminous and massive stars discovered yet.